Welcome in the journey of time. Tonight, we'll unfold another page of history. Perhaps you're lying in bed, or maybe you've simply decided to let the past accompany you for a while. Where are you joining me from tonight? Leave a comment if you'd like. I always enjoy hearing about your corner of the world. And what time is it for you now? If you find this slow and thoughtful stories of those who came before us brings you a sense of peace and comfort, I'd be honored if you like and subscribe. So, here's the story. The Measurer's Gaze, an epic of the Earth's true shape. Before names, before numbers, there was a comparison. A consciousness, primitive and nascent, stirred within the mind of a being who was more than ape, but not yet man. This consciousness was me. I was not born, I was realized. My first home was the space between a stretched thumb and a forefinger, the gap between a footfall and the next, the length of a forearm from elbow to fingertip. They did not know me, us Metron, but they felt my presence when they looked at two trees and wondered which would make a better spear, or when they gazed across a river and judged the distance a leap could carry them. My first true awakening happened in the mind of a woman I would later call On. The tribe lived in a lush valley, a world bounded by jagged teeth of mountains on one side and a wide, snarling river on the other. The sky was a bowl of beaten copper, and the earth was all they knew. One day, On's child, a boy with curious eyes, vanished. He had chased a grasshopper beyond the standing stones that marked the safe ground. The hunters returned at dusk, their faces grim. They spoke of the sun-swallowing plains beyond the river, a place where the spirits of the air stole children. On did not wail. She did not accept. A fire, kindled by a mother's terror, ignited in her soul, and in that fire, I was forged. She stood at the river's edge, the muddy water pulling at her ankles. The far bank seemed a world away, a smear of green and brown under the fading light. The hunters gestured, their arms sweeping to indicate vast, unknowable distances. Too far, their gestures said, the spirit of the river is hungry. But On looked not with fear, but with me. She picked up a long, straight branch that had been polished smooth by the current. She laid it on the ground. Then she took another step, laid another branch end to end. She was creating a copy of the distance, a representation. With each branch, she moved a piece of the far shore closer to her feet. The hunters watched, first with confusion, then with a dawning, superstitious awe. She was performing a kind of magic. She counted the branches, 12. She then walked back to the tribe's hearth and laid 12 identical branches in a line. She looked at this line, this tangible echo of the river's width. She looked at the strongest hunter, a man named Goran. She pointed to the line of branches, then to the river. She made a swimming motion. Her meaning was unmistakable. This distance. Can you cross it? Goran looked from the miniature river to the real one. The abstraction made the immense manageable. The unknown became a known quantity of 12 branches. He grunted, a new light in his eyes. He nodded. The next morning, Goran swam the river. He did not find the boy that day, but he returned with news. The far shore was not the sun-swallowing plains. It was more grassland like their own. The world had just doubled in size. And I, Metron, had been born. I was the bridge between the known and the unknown, the tool that made the vast and terrifying world comprehensible, one measured step at a time. The shadow in the well. The centuries flowed like the Nile itself, a great brown life-giving serpent sliding through the desert. My consciousness had drifted, a seed on the wind, from one intuitive mind to another. I was in the knotted chords of the Andean Quipucamayaks, in the aligned stones of Karnak, in the standardized bricks of the Indus Valley. But I found a new, potent home in the land of Kemet, which others would later call Egypt. Here, I was no longer just a tool for survival. I was an instrument of power and order, Ma'at. The pharaoh was the embodiment of Ma'at, and I was the means to impose it upon the chaotic world. My name became the cubit, a length of forearm from elbow to fingertip, meticulously carved into black granite rods kept in the temples. With me, they built pyramids that kissed the sky, and with me, they redrew the fields after the Nile's annual inundation washed the boundaries away. My vessel in this age was a man named Senenmut, a royal architect and the chief steward of the pharaoh Hatshepsut. He was a man of sharp angles and a sharper mind, his eyes holding the calm certainty of geometry. I resided within him, not like a separate spirit, but like a refined instinct. When he looked at a block of limestone, he did not see a rock. He saw a potential cube, its dimensions already present, waiting to be revealed by the chisel. We were in Thebes, the air thick with the dust of construction and the scent of lotus blossoms. The sun, the god Radiallahu, was a punishing, brilliant force. Senenmut was overseeing the raising of Hatshepsut's magnificent mortuary temple at Deir el-Bahari, a symphony in stone that seemed to grow directly from the cliffs. But a smaller, more profound problem occupied his mind. A Greek traveler, a talkative man named Thales from Miletus, had come to the court. He was full of strange ideas. Over cups of date wine, he had posed a question to the Egyptian priests. How high, he had asked, is the shadow of the pharaoh? The priests had scoffed. The pharaoh casts no shadow. He is a god, filled with the light of Radiallahu. Thales, undeterred, had rephrased. How high, then, is the sun? This question had intrigued Senenmut. He found Thales standing by a deep, stone-lined well in the temple precinct. It was the day of the summer solstice. The sun reached its zenith, and for a few precious moments, its light speared directly down into the well's depths, illuminating the water at the bottom without casting a shadow on the walls. "Look," Thales said, his voice eager. He had planted a vertical rod into the ground nearby. Here in Sienne, at this exact moment, the sun is directly overhead. But in your city of Alexandria, to the north, it would not be. A vertical rod there would cast a shadow. Senenmut understood instantly. Aha surged within him, connecting concepts. 2 locations, 1 light source, angles. 2 points on the earth, Senenmut murmured, his gaze shifting from the well to the rod. The sun's rays are parallel. The angle of the shadow in Alexandria would be the same angle as the difference between the 2 locations on the Earth's curvature, Thales finished, his eyes alight. This was a leap of cosmic scale. We had been measuring the Earth in cubits, in plots of land, in the heights of pyramids. Now we were measuring the Earth itself. Senenmut, with the pharaoh's resources, enacted the experiment. He dispatched trusted surveyors to Sienne to confirm the well phenomenon. In Alexandria, on the next solstice, he personally oversaw the planting of a perfectly vertical gnomon, a measuring staff. He waited, the sun beating down on his bare head. The shadow, a sliver of darkness, grew shorter and shorter until noon. It did not vanish. It measured just over 7 degrees. The atmosphere was electric, charged with intellectual triumph. Senenmut could feel the shape of the world beneath his feet. It was not a flat, infinite plane. It was curved. He had the 2 points and the angle. Now he needed the distance between Sienne and Alexandria. This was my domain. He dispatched the Harpedonopti, the rope stretchers, the master surveyors of Egypt. Their journey was an epic in itself. They walked the distance, not with branches, but with a calibrated rope of knotted, stretched papyrus, kept taut to avoid sagging. They counted the days. They corrected for the winding path of the Nile. They factored in the topography. It was a monumental effort of applied belief, a faith in my power. The number came back, 5,000 stadia. That night, Senenmut sat in his chamber. The air was cool, carrying the distant sounds of the city. A single oil lamp cast flickering shadows that danced like the ghosts of old ideas. On a sheet of papyrus, he drew a vast circle. He marked 2 points on it. He drew lines from these points to the center, and lines representing the parallel sun rays. The geometry was elegant, pristine. The ratio of the 7-degree angle to the full 360 degrees of a circle must be the same as the ratio of the 5,000 stadia to the full circumference of the Earth. His stylus scratched the final calculation. The number that emerged was staggering. 252,000 stadia. A value so immense it was nearly incomprehensible. The room seemed to shrink around him. The world he knew, the vast empire of Egypt, was suddenly a small patch on the surface of an unimaginably large sphere. He walked out onto his balcony, looking at the star-dusted sky. The earth was no longer just the ground beneath his feet. It was a body, a thing with dimensions. It had a size. I, Metron, had given it that size. We had taken the measure of our home. It was the first, greatest adventure, and it had only just begun. The world was no longer a flat disk under a dome. It was a giant ball hanging in a void, and we knew, for the first time, just how giant it was. The Keeper of the Scrolls. The knowledge Senenmut and Thales had unearthed did not perish in the desert sands. I, Metron, felt that calculation resonate through the centuries, a subtle vibration in the fabric of human understanding. The great sphere of the world now had a number, a dimension, and that number demanded guardians. My consciousness drifted north, across the wine-dark sea, to a city that was becoming the very brain of the world, Alexandria. I found a new home, not in the mind of a king or a conqueror, but in the heart of a librarian. His name was Eratosthenes of Cyrene, a man whose frame was slight and whose eyes, perpetually squinting from long hours in lamplight, held a universe of curiosity. He was the head of the great library, a position that made him the custodian of all known wisdom. His chambers were a beautiful chaos of piled papyrus and stacked wax tablets, the air thick with the smells of ink, aged paper, and slow-burning olive oil. It was here, amidst this organized delirium of knowledge, that the ghost of Senenmut's calculation found its way to him. He read the accounts of the Egyptian rope stretchers, the angles of the shadows. But Eratosthenes was a man of rigorous precision, a soul who worshipped at the altar of accuracy. The old number, 252,000 stadia felt like an approximation, a magnificent guess. He believed I, Metron, deserved a more perfect expression. His opportunity came not from a well, but from an obelisk. The city of Sienne, now called Aswan, still held its perfect solar alignment. But Alexandria had its own perfect vertical, the towering needle of an obelisk dedicated to a forgotten pharaoh. On the day of the summer solstice, Eratosthenes, accompanied by a young, skeptical apprentice named Philon, emerged into the blinding white heat of the public square. The atmosphere was a stark contrast to the quiet of the library. The air vibrated with the cries of merchants, the clatter of cartwheels on stone, the smell of spiced meat and human sweat. The obelisk, a shaft of red granite, stabbed at the azure sky. Eratosthenes, ignoring the jostling crowd, directed Philon to set up the measuring instrument, a bronze disc called a scaphe, calibrated with exquisite care into 360 degrees. Tell me when the shadow is at its absolute shortest. The moment it begins to lengthen again, you must tell me. Philon, his tunic sticking to his back, knelt, his eye fixed on the sharp line of the shadow cast by the obelisk's peak onto the graduated disc. The sun climbed. The shadow shrank. The tension was palpable. A tight string pulled between the two men and the cosmic clockwork overhead. "Now!" Philon shouted, his voice cutting through the din. "It is shortest now!" Eratosthenes, his own hands steady despite the excitement thrumming in his veins, leaned over the scaphe. The shadow's tip fell not on a round number, but on a precise, beautiful fraction. 1/50th of a circle, he breathed, his voice full of reverence. 7 1/5 degrees. This was the first refinement. The Egyptian measurement had been close, but this was exact. The difference in angle between Alexandria and Sienne was precisely 1/50th of a circle. Therefore, the distance between the two cities must be 1/50th of the Earth's total circumference. But the second part of the equation, the distance between the cities, remained a problem. The old measurement of 5,000 stadia by the rope stretchers was an estimate, a product of a long, arduous journey. Eratosthenes needed something better. He needed a professional. He summoned Bion, the royal beimatist. Beimatists were a special class of surveyor, human instruments trained from youth to walk with an unnaturally consistent pace. They could measure vast distances by counting their steps, their stride length calibrated to a science. Bion was a man of few words, with a leathery face etched by sun and wind, and legs that were like gnarled oak. Eratosthenes gave him his commission. Walk from Alexandria to Sienne. Count every step. Do not follow the river's whims. Walk the most direct route you can. I do not need a story of your journey. I need a number. Bion nodded, a single curt gesture, and departed. His journey was a silent epic of endurance. He walked through blistering days and cold nights, his mind a perfect metronome of left, right, left, right. He crossed deserts where the heat haze made the world waver, and climbed rocky escarpments that tested the consistency of his stride. He did not see the beauty of the landscapes. He saw only a line, a geodesic of intent, stretching across the earth. He was the embodiment of my will, a living, breathing measuring rod. Months later, Bion returned to the library. He was thinner, dustier, but his eyes held the calm certainty of a completed task. He stood before Eratosthenes' cluttered desk and did not sit. "The distance," he said, his voice a dry rasp, "is 5,040 stadia." Eratosthenes looked at him, then at the papyrus on his desk. The calculation was now simple, elegant, divine. He took his stylus. If 5,440 stadia represents 1/50th of the whole, then the whole circumference is 5,040 multiplied by 50. The stylus scratched the final figure, 252,000 stadia. A slow smile spread across Eratosthenes' face. It was the same number the Egyptians had found, but it was not the same. Theirs had been an estimate, a brilliant guess. His was a confirmation, a refinement, a truth verified by two separate, rigorous methods: the perfect geometry of the heavens and the relentless counting of a human foot. The convergence was the beauty. It meant the world was not only spherical, but also measurable, knowable, and subject to the relentless, beautiful logic of mathematics. He looked up at Bion and Philon. "We have weighed the world," he said, his voice thick with emotion, "and we have found it to be a thing of perfect proportion." In that moment, I, Metron, grew stronger. I was no longer just a tool for building or a trick for crossing rivers. I was the language in which the universe spoke its secrets. And in the great library of Alexandria, for a fleeting, glorious moment, we were listening. The silk and the gnomon. The flame of Alexandria, though brilliant, was not eternal. I felt the great library's light dim, its scrolls turning to dust, its wisdom fragmenting and scattering to the winds. The precise, beautiful sphere of Eratosthenes began to blur in the human imagination, slowly flattening under the weight of dogma and forgotten texts. My consciousness became a ghost, a whisper carried on trade routes and in the saddlebags of scholars fleeing a dying world. My journey east was long and arduous. I traveled with Nestorian monks, their minds bent on theological disputes, yet their caravans were my vessel. I lingered in the great bazaars of Ctesiphon, where the air was thick with the scent of spices, dyes, and the bitter tang of ink. For centuries, I was a dormant seed, waiting for the right soil. I found it in the fertile, intellectually voracious world of the Abbasid Caliphate. In the House of Wisdom in Baghdad, a city that hummed with a new kind of energy, I was reborn. Here, Greek, Persian, Indian, and Chinese knowledge swirled together in a great alchemical crucible. My name was translated, my concepts debated. I was no longer just Metron, I was Ilm el-Handasa, the science of geometry. My new vessel was a man named Al-Mamun, the Caliph himself. He was not a scholar in the dusty, isolated sense. He was a ruler of immense power and insatiable curiosity, a man who understood that knowledge was the ultimate currency of empire. He dreamed not just of ruling the world, but of understanding it. I resonated with his ambition, for it was my own. The trigger was a practical, earthly problem, the dispute over a land inheritance. Two brothers from the fertile plains of the Tigris argued over a field, its boundaries washed away by a seasonal flood. The local judges, using rough estimates and conflicting testimonies, could not settle the matter justly. The case came before the caliph. Al-Mamun listened, his expression impassive, but I could feel the spark of an idea ignite within him. The old methods were inadequate. The world needed to be measured again, with a new rigor to impose a divine and mathematical order upon human affairs. He summoned his chief astronomer, a meticulous man named Al-Khwarizmi, whose face was a roadmap of careful thought. They stood on the highest balcony of the caliph's palace, looking out over the sprawling city, a mosaic of whitewashed buildings and glittering canals under the hard, clear sky. "The number of Eratosthenes," Al-Mamun began, his voice low and intent. "Is it true? Is his calculation of the Earth's girth a fact?" Al-Khwarizmi bowed his head slightly. "The geometry is sound, Commander of the Faithful, but the initial measurement, the stadion, its length is debated. The Greeks themselves could not agree on its standard. We have inherited a magnificent calculation built upon a foundation of sand. Then we will rebuild the foundation," Al-Mamun declared, his gaze sweeping across the horizon. "We will not rely on the footsteps of a single man or the memory of an Egyptian well. We will measure a degree of the earth itself. We will carve a meridian across the desert and take its true measure." This was a project of staggering scale and ambition. It would be my greatest embodiment yet. Al-Mamun assembled 2 teams of his finest scientists, surveyors, and mathematicians, the Munajimon. One team, led by the brothers Ahmad and Mohammed ibn Musa, would journey north. The other, under the stern gaze of the geographer Al-Farghani, would travel south. Their mission, to find a vast flat plain and measure the length of 1 degree of latitude. The location chosen was the sun-scorched plain of Sinjar, a place where the earth was flat as a polished brass plate, and the sky was an immense empty bowl. The atmosphere was one of extreme isolation and profound focus. The wind was a constant, dry whisper, carrying fine dust that coated everything: instruments, robes, the back of the throat. The method was one of exquisite, painstaking precision. They used long, calibrated wooden rods, each checked against the royal standard cubit. They did not walk. They laid the rods end to end with the care of men assembling a priceless mosaic. Each junction was checked for alignment, not just horizontally, but vertically, using water levels to ensure the path was truly level and not following some slight, deceptive slope of the land. The vibe was one of a sacred pilgrimage. By day, they worked under the punishing sun, their progress measured in agonizingly slow increments. By night, they slept in tents, the air inside thick and hot, while outside the stars blazed with a cold, indifferent clarity. They took astronomical readings every night, using massive brass astrolabes and finely graduated quadrants to determine their exact latitude by the altitude of the pole star. They were not just measuring the Earth, they were triangulating their position between the dust at their feet and the fixed points of the celestial sphere. Ahmad ibn Musa, a man with a poet's soul trapped in a scientist's mind, kept a journal. One evening, his hand aching from a day of aligning rods, he wrote by the flickering light of an oil lamp. "We are tracing the curve of the world with these sticks of wood. It is a humbling and magnificent endeavor. Each rod we lay is a prayer to the order of creation. We are proving that God's world is not a chaotic mystery, but a written text, and its language is number." After weeks of this relentless, meticulous work, the 2 teams converged. The data was collated, the numbers crunched in a storm of abacus beads and scratching pens. The result was a new, definitive value for the length of 1 degree of the Earth's meridian. Al-Khwarizmi presented the finding to the Caliph in the cool, serene quiet of the palace library. The air smelled of rosewater and old paper. "Commander of the Faithful," he said, unrolling a vast vellum scroll covered in dense, beautiful script and complex diagrams. We have measured the Earth. 1 degree of its meridian is 56 2/3 Arabic miles. Therefore, the full circumference of the world is 20,400 of these miles. He paused, letting the number hang in the quiet room. This is smaller than the calculation of the Greeks. Their stadion was clearly shorter than our mile. Eratosthenes was correct in his geometry, but we have corrected his unit. The world is knowable, and now it is known with a precision never before achieved. Al-Mamun did not smile. He simply nodded, a deep, profound satisfaction settling upon him. The disputed field was divided with a new, unassailable authority based on this grander measurement. But the legacy was far greater. In the deserts of Sinjar, I, Metron, had been forged anew. I was no longer a Greek idea. I was a universal truth. The Caliph had not just measured the earth. He had demonstrated that through rigorous, collective, and funded inquiry, humanity could unlock the deepest secrets of its home. The adventure of measurement was now a state-sponsored global pursuit. The world had shrunk, not in size, but in its mystery. And it was only the beginning. The legacy of Al-Mamun was a beacon that burned for centuries. Its light carried by caravans of scholars across the Islamic world and into the budding universities of a Europe slowly emerging from its long intellectual slumber. I, Metron, felt my presence diffuse, becoming a foundational principle in the minds of men who studied the Almagest and the commentaries of Al-Farghani. The earth was a sphere. This was settled knowledge among the learned. Yet, a new and profound puzzle began to gnaw at the edges of this certainty. It was a problem of navigation, of practical geometry on a curved surface. A ship sailing a constant compass course did not trace a straight line on a globe. It spiraled towards the poles in a loxodromic curve, a path that was inefficient and confounding to sailors trying to plot the shortest distance between two ports on a flat parchment chart. My consciousness, ever drawn to such conundrums, found a new vessel in the damp, chilly air of a Flemish workshop. His name was Gerardus Mercator, a man whose hands were stained with ink and whose mind was a crucible where art, science, and commerce melded. He was an engraver, a calligrapher, and a cosmographer, a man who made his living by selling the world, quite literally, in the form of maps. The atmosphere in his workshop in Leuven was a stark contrast to the sun-baked plains of Sinjar or the scholarly quiet of Baghdad. It was a place of intense, focused industry. The air was laced with the acidic bite of etching agents and the rich, earthy smell of printing ink. The rhythmic tap-tap-tap of the burin against copperplate was the soundtrack of his life. Maps in various stages of completion hung from lines, their paper rustling like the whispers of distant lands. Mercator's problem was not the size of the earth, but its representation. How could one project the skin of a sphere onto a flat sheet without tearing, compressing, or grotesquely distorting its features? The existing maps, the Portolan charts, were useful for coastal navigation but became wildly inaccurate over open ocean. They preserved local directions but sacrificed global shape. I stirred within him not a desire for a single grand measurement, but an obsession with a mathematical transformation. He spent nights bent over his desk, the pool of light from a single whale oil lamp illuminating complex calculations. Scraps of paper covered in trigonometric functions and geometric proofs littered the floor like fallen leaves. His wife would often find him asleep, his head resting on a half-finished chart of the New World. The breakthrough did not come in a single blinding flash. It was a slow, grinding dawning, built upon the work of others, a cumulative effort that I, Metron, was orchestrating across generations. He studied the geometry of loxodromes. He understood that to make a rhumb line, a line of constant compass bearing, appear as a straight line on a map, the lines of longitude, which converge at the poles on the globe, must be rendered as parallel lines on the flat map. But this simple act of pulling the meridians apart created a catastrophic distortion. The higher latitudes were stretched horribly out of shape. Greenland would appear larger than South America. This was cartographic heresy. The solution was one of breathtaking, counterintuitive genius. It was a compensation, a deliberate, calculated distortion to cancel out the first one. He realized that to preserve the correctness of local angles and shapes, the vital requirement for navigation, he had to progressively stretch the distance between the parallels of latitude as one moved away from the equator. The stretching of the north-south scale had to exactly match the stretching of the east-west scale caused by the fanned-out meridians. The moment of final realization was a quiet, profound one. It was late. The city of Louvain was asleep. The only sound was the soft hiss of the lamp and the scratching of his quill. He was working on a new map of Europe. He applied his formula, increasing the spacing of the latitudes for Norway, for Iceland. He saw the coastline of Scandinavia, which on previous maps had been a cramped, squashed thing, now unfold into its true elongated proportions. The angles at every cape, every bay were perfect. A ship's captain could draw a straight line from Lisbon to the Azores on this map, follow that constant bearing with his compass, and arrive exactly where the map said he would. He leaned back, his body aching with fatigue, but his spirit soaring. He had done it. He had not measured the earth with rods and stars. He had tamed it with mathematics. He had created a grid, a new skin for the world, where the brutal, complex reality of a sphere was translated into the elegant, navigable logic of a flat plane. In 1569, he published his great world map, Nova et aucta orbis terra descriptio ad usum navigantium emendate accommodata, a new and augmented description of the Earth corrected for the use of navigators. It was a monumental sheet of printed paper, over 6 feet by 4 feet, a vast and strange-looking world. The Americas were slimmer, the Pacific Ocean impossibly vast, the polar regions bloated beyond recognition. To the untrained eye, it was a distorted, ugly thing. But to the mariner, it was a key to the oceans. It was a tool of pure function, a chart that spoke the language of the compass. Mercator had given them a world they could sail by logic, not just by dead reckoning and luck. I, Metron, had been transformed. I was no longer just the measure of physical distance. I was now the principle of projection, the translator between the curved reality of the cosmos and the flat necessity of human perception. With Mercator's chart, the age of exploration was handed its most powerful tool. The Earth was not just known, it was now rootable. And this new, flattened version of the sphere would itself become the stage for the next great act in my story, a battle over the very shape of the world I had helped to define. The sphere, it seemed, was not quite a sphere after all. The squeezed orange. The world, rendered flat and navigable by Mercator's genius, was now being crisscrossed by European ships with an unprecedented confidence. I, Metron, sailed with them, my presence felt in the precise logbooks of captains and the improved design of their nautical instruments. The spherical Earth was a settled fact, a cornerstone of celestial navigation. Yet, a subtle discordance began to emerge, a whisper of a flaw in the grand classical model. The whisper originated not from the sea, but from the pendulum. In the bustling, intellectually fertile city of Paris, a new age of precision was dawning. The Academy of Sciences, a gathering of the finest minds, sought to impose order upon the universe through meticulous experiment and quantification. It was here I found my next vessel, John Richer, an astronomer and cartographer of humble origins but impeccable observational skill. Richer was a man of methodical patience, his world defined by the tick of a clock and the crosshairs of a telescope. In 1671, the Academy entrusted him with a vital mission. To improve longitude determination, he was to travel to Cayenne, a French colony perched on the sun-baked northern coast of South America, just 5 degrees north of the equator. His task was to observe the parallax of Mars during its close approach to Earth, and to make precise stellar observations that would tie the heavens to the map. The atmosphere in Cayenne was a shock to his system. After the damp, temperate climate of Paris, the equatorial air was a thick, wet blanket, heavy with the scent of rotting vegetation, salt, and exotic blossoms. The heat was a physical force, and the light was a blinding white glare. Richard set up his portable observatory, a sturdy tent housing his most precious cargo, a state-of-the-art pendulum clock, regulated to keep perfect time in the latitude of Paris. From the very first day, a profound and unsettling anomaly presented itself. The clock, his faithful arbiter of cosmic rhythm, was wrong. It lost time. Not by a lot, a mere 2.5 minutes each day, but with a stubborn, undeniable consistency. Richer, a man who lived by the sanctity of measurement, was horrified. He checked for errors in the clock's mechanism, for the effects of the humidity and heat on its metal parts. He painstakingly leveled the instrument. The error remained. Puzzled, he began a series of ancillary experiments. He decided to measure the length of the seconds pendulum, a pendulum designed to have a swing of exactly 1 second. In Paris, this was a standard length, carefully defined. He set up a simple bob on a fine wire and adjusted its length until its tick-tock matched the beat of the star's transit across his meridian. The result was another shock. The pendulum that beat a perfect second in Cayenne was significantly shorter than its Parisian counterpart. This was not a mere mechanical curiosity. This was a physical impossibility within the accepted worldview. The period of a pendulum's swing depends on only 2 things, its length and the force of gravity. If the pendulum was shorter here to keep the same time, it could mean only one thing. The force of gravity was weaker at the equator. Richer's mind raced, connecting this to other fainter whispers. The accounts of travelers who felt strangely lighter in the tropics. The theoretical musings of men like Huygens and Newton, who were beginning to propose that the Earth might not be a perfect sphere, but a spheroid flattened at the poles, bulging at the equator, an oblate shape caused by its rotation. On a bulging sphere, a point at the equator is farther from the center than a point at the pole. The force of gravity, weakening with distance, would be less. A pendulum would swing more slowly, unless it was shortened. The atmosphere in his tent shifted from one of tropical languor to one of electric, terrifying discovery. The air itself seemed to hum with the implications. He was not just measuring stars. He was weighing the Earth and finding it wanting in its perfection. The very ground beneath his feet was not what the philosophers of Paris believed it to be. The Earth was not a perfect sphere. It was a squeezed orange, deformed by its own spin. For weeks, Richter repeated his experiments, his hands trembling not from the heat, but from the magnitude of what he was uncovering. Each confirmation of the shorter pendulum, each tick of the lagging clock was a nail in the coffin of the classical ideal. He felt a profound loneliness. He was a single man, in a remote and fever-ridden outpost, holding a secret that would shake the foundations of cosmology. When he finally returned to Paris in 1673, he brought with him not just stellar data, but his meticulous logbooks detailing the anomalous pendulum. He presented his findings to the Academy. The reaction was not the triumph he had naively hoped for. It was skepticism, bordering on hostility, particularly from the aging and formidable Giovanni Domenico Cassini, the director of the Royal Observatory. Cassini, a master of positional astronomy, had built his career on the perfection of the celestial spheres. He favored a prolate spheroid, an Earth elongated at the poles like an egg. Richter's data from Cayenne directly contradicted this. The meeting room of the Academy was thick with tension. The air, usually scented with wax and old books, was now charged with intellectual combat. "Your clock was affected by the voyage," Cassini declared, his voice dripping with condescension. "The tropical heat warped its parts. This weaker gravity is a fantasy born of faulty equipment." Richter stood his ground, his voice quiet but firm. "I accounted for the heat. I measured the pendulum itself. The effect is real. The Earth is oblate." The debate raged for decades, a bitter, international dispute that became known as the Battle of the Figures of the Earth. Metron, was at the very heart of it. Richter's single, precise observation in the sweltering heat of Cayenne had opened a fissure in human understanding. The question was no longer how big the Earth was, but what shape it was. The adventure of measurement had plunged into a new, more complex dimension. The quest to map the world was now a quest to feel its true, imperfect form. And the only way to settle the argument was to measure the Earth itself, with unprecedented cruelty and precision, along a meridian arc that stretched from the frozen north to the sun-baked south. The fate of Newtonian physics and Cartesian cosmology hung in the balance. The King's Meridian. The schism Richter had opened festered for half a century, a persistent, nagging wound in the body of European science. The battle of the figures of the Earth was not fought with swords, but with treatises, insults, and competing sets of data. In one corner stood the Cartesians, followers of Cassini, clinging to the prolate, egg-shaped Earth. In the other, the Newtonians, armed with the powerful new tool of calculus and the principle of universal gravitation, championed the oblate, flattened sphere. Metron, thrived in this contentious atmosphere. The very existence of the debate was a testament to my centrality. The question was no longer abstract. It was a physical problem demanding a physical solution. The answer lay not in the stars alone, but in the mud, rock, and ice of the Earth itself. The resolution came from an unlikely source: the French crown. In 1735, Louis XV, advised by the reform-minded minister of the Navy, the Comte de Maurepas, was persuaded that the glory of France was tied to the resolution of this great scientific question. The king gave his blessing, and the French Academy of Sciences organized the most ambitious geodetic expedition the world had ever seen. Not one, but 2 missions would be dispatched to measure a degree of latitude at the most extreme points possible. One to the equatorial bulge near Quito in the Viceroyalty of Peru, and another to the frozen wastes of Swedish Lapland near the Arctic Circle. By comparing the length of a degree at the equator and the pole, the true figure of the Earth would be revealed. My consciousness split, a twin flame igniting in the hearts of the leaders of these two parties. For the Peruvian expedition, my vessel was Charles Marie de la Condamine, a man of boundless energy, sharp wit, and a stubbornness that bordered on folly. For the Lapland mission, it was Pierre-Louis Moreau de Maupertuis, a brilliant mathematician and physicist, a confident and charismatic figure who had already thrown his lot in with the Newtonian cause. The departure of the two expeditions from France was a moment of high drama. The Peruvian team, which also included the astronomers Louis Godet and Pierre Bouguer, was vast, a small army of scientists, artists, and assistants, their ship laden with the finest instruments money could buy, zenith sectors, quadrants, and long, precision-made iron chains for measurement. The atmosphere was one of grand adventure, tinged with a naivete about the trials to come. Maupertuis's Lapland party, in contrast, was lean and focused. They understood their task was to be a swift, surgical strike into the north to provide a clear comparison. Their departure was quieter, more businesslike, but no less determined. We follow La Condamine first. The journey to South America was an ordeal in itself. Months at sea, storms, sickness. When they finally arrived at the port of Manta, the reality of their task struck them with the force of a physical blow. They were not in the civilized world of European salons. They were in the Andes, a realm of titanic scale and primal power. The air was thin and cold, despite their proximity to the equator. The sun was a fierce, blinding disk in a sky of impossible blue. The mountains were not the gentle rolling hills of France. They were shattered, jagged teeth of rock, veiled by swirling mists and prone to violent tremors. The vibe was one of sublime terror and overwhelming majesty. They had to trace a meridian arc over this terrain, a task comparable to measuring the wrinkles on a giant's face while he was sleeping. Their base of operations became the small city of Quito, a picturesque town of whitewashed churches and red-tiled roofs nestled in a high valley. But its charm quickly faded. The team was plagued by internal strife from the outset. Godin, the nominal leader, was aloof and bureaucratic. Bouguer was a perfectionist, easily frustrated by the smallest error. La Condamine was a firebrand, impatient and combative. I, residing within him, felt the constant friction, the clash of egos in this pressure cooker environment. Their method was triangulation. They would climb a mountain peak, Pambamarca, Pichincha, Cotopaxi, their lungs burning in the thin air. They would erect a signal, a large wooden pyramid, often illuminated at night by bonfires. Through the massive, exquisitely calibrated zenith sector, they would measure the angle between this signal and the fixed stars to determine their precise latitude. Then they would measure the baseline distance between 2 points with the iron chains, a process of agonizing slowness over broken ground. This baseline would become the foundation for a vast imaginary web of triangles spanning hundreds of miles of the most difficult terrain on Earth. The conditions were inhuman. They suffered from soroche, altitude sickness, its symptoms a constant companion of headache and nausea. They faced bitter cold on the high peaks and sweltering heat in the valleys. They were cheated by local officials, threatened by bandits, and caught in the middle of a local rebellion. Their artist, Jean-Baptiste Morisot, sketched them not as heroic savants, but as haggard, bearded men in ragged clothes, their instruments their only remaining symbols of civilization. One day, while measuring a baseline on the Yaruki Plains, a dispute between Condamine and Bouguer over a minuscule alignment error erupted into a screaming match that echoed across the empty landscape. The two men, who had started as colleagues, were now bitter enemies, barely able to be in the same room. The expedition was tearing itself apart. I felt my purpose being subsumed by pettiness. The grand quest to measure the Earth was being derailed by the very human flaws of the measurers. Yet they persevered. Driven by a mixture of sheer stubbornness, professional pride, and a flickering sense of the historic importance of their task, they continued to lay their triangulation points, one agonizing mountain at a time. Years turned into a decade. They were no longer young men on an adventure. They were aging, weathered fixtures of the Andes, their goal a distant, almost mythical horizon. The measurement of the Earth was proving to be a task that demanded not just intelligence, but an almost superhuman endurance. The fate of Newton's theory rested on the weary shoulders of these squabbling, suffering men, clinging to their zenith sectors in the high, thin air of the mountains. The answer was there, in the angles and the distances, if only they could survive long enough to find it. The frozen degree. While Condamine and his comrades battled the vertiginous heights and their own fractious tempers in the Andes, the northern counterpart of their mission was unfolding under a different but no less brutal set of extremes. I, Metron, my consciousness a flickering candle in the mind of Pierre-Louis Moreau de Maupertuis, found myself in a world bleached of color and softened by a profound, penetrating cold. The Lapland expedition arrived in the city of Tornio on the border of Sweden and Finland in the summer of 1736. The initial impression was deceptively pleasant. The sun, which barely dipped below the horizon, cast a perpetual golden glow over the pine forests and the wide, sluggish river. The air was clean and sharp, filled with the scent of pine resin and damp earth. But this was the briefest of respites. Maupertuis, a man of elegant Parisian habits, knew their work must be completed before the Arctic winter descended, a season he had only read about in terrifying accounts. Their task was identical in principle to the Peruvian mission, to measure the length of a degree of latitude. But here, the challenges were inverted. Instead of towering, unstable mountains, they faced a landscape of relentless flatness, a vast boggy plain choked with stunted pines and veined with icy streams. Instead of altitude sickness, they faced the psychological weight of the endless summer day, which robbed them of night's rest, and the impending threat of the polar night. Maupertuis's team was smaller, more cohesive. It included the Swedish astronomer Anders Celsius, a man of quiet competence who had already devised his temperature scale, and the French mathematician Alexis Clairaut, a young prodigy whose mind was as sharp and cold as the coming ice. The atmosphere was one of focused cerebral urgency. There was no time for the grandstanding and disputes that plagued the southern team. The Arctic was a strict, unforgiving master. Their chosen meridian arc ran from the hill of Kitasvara near Tornio to the peak of Avasaksa further north. The distance was shorter than the Peruvian arc, but the environment was no less hostile. To measure their baseline, they chose the frozen surface of the Tornio River. The vibe during this operation was one of surreal beauty and constant peril. The world was a monochrome of white snow and black fir trees, the silence broken only by the crunch of their boots and the howl of the wind that swept down from the pole. They laid their measuring rods, not chains, but carefully calibrated wooden toises, on the ice. The cold was so intense it made the metal of their instruments painful to touch. Their breath plumed in great frozen clouds, and the moisture from their bodies condensed and froze inside their woolen clothing. They worked in shifts, their beards and eyebrows crusted with ice, their fingers growing numb and clumsy despite thick gloves. A single misstep could send a man plunging through a weak spot in the ice into the black, lethal water below. I, Matron, felt the precariousness of their endeavor. They were measuring the earth on a fragile pane of glass, with death waiting just beneath. The triangulation phase began as the summer waned. They built great signal pyres on the hilltops, mounds of tar and wood that, when lit, became beacons of defiant human order against the vast, empty darkness. Climbing Avasaksa in the autumn was a trial. The ground was a treacherous mixture of rock and slick, frozen lichen. The wind whipped across the summit with a force that threatened to pluck them from their feet and send them tumbling into the void. Celsius and Maupertuis would take turns at the zenith sector, their bodies huddled against the instrument for stability, their eyes watering in the gale as they tried to fix the position of a star through the crosshairs. The moment the final observation was recorded, a palpable shift occurred. The sun, which had been their constant companion, began to vanish. The golden summer light faded, replaced by long blue twilights that deepened daily. The first snows fell, not as a gentle dusting, but as a relentless horizontal blizzard. The world closed in around them. The vibe in their small log cabin in Tornio transformed from one of scientific endeavor to one of primal survival. The Arctic winter was an entity in itself. The darkness was absolute, a heavy blanket that smothered sound and hope. The cold became a physical presence in the room, seeping through the chinks in the log walls, freezing the ink in their pots, and making the very air they breathed feel like shards of glass in their lungs. The silence outside was punctuated by the creaking of the frozen river and the lonely howl of wolves. Inside, the atmosphere was thick with wood smoke and the tension of men confined too long in close quarters. They suffered from scurvy, their gums bleeding, their bodies weakening. It was during this long, dark trial that the data was processed. By the flickering light of a seal oil lamp, with the wind screaming its lament outside, Maupertuis and Clairaut crunched the numbers. The triangles were solved, the angles compiled, the baseline extended across the meridian arc. The calculation was a lifeline, a thread of pure reason, connecting them to the world of light and learning they had left behind. Finally, one bleak morning, the result emerged from the columns of figures. Maupertuis looked up from the parchment, his face gaunt in the lamplight, his eyes burning with a fierce, triumphant light. "The degree here at the Arctic Circle," he announced, his voice hoarse but clear, "is longer than Picard's measurement in France." Significantly longer. The room fell silent, save for the crackle of the fire. Clairaut nodded slowly, a grim smile on his face. Celsius let out a long, slow breath that misted in the frigid air. The implication was inescapable. If a degree of latitude grew longer as one approached the pole, it meant the lines of longitude were converging more rapidly. The Earth was not a sphere where all degrees were equal. It was fatter at the equator, compressed at the poles. The Earth was oblate. Newton was right. In that frozen cabin, surrounded by darkness and despair, they had found a truth that would reshape the world. Maupertuis, who would later boast that he had flattened the Earth and the Cassini's, knew his mission was a success. They had endured the ultimate physical hardship to prove an abstract mathematical principle. The Lapland expedition had been a brutal, swift, and conclusive strike. As they waited for the sun to return, they knew they carried back to Paris not just data, but victory. The battle of the figures of the earth had been won in the silent, frozen darkness of the Arctic. The tangled web. The triumphant return of Maupertuis and his men to Paris in 1737 was a spectacle of intellectual victory. They were hailed as heroes who had braved the icy jaws of the Arctic to confirm the Newtonian universe. I, Metron, basked in the clarity of their result. The Earth was oblate. The debate, it seemed, was settled. But in the distant Andes, no such clarity existed. For La Condamine, Boger, and Godin, the long years were stretching into a decade of toil, sickness, and acrimony. The initial mission had fractured into 3 separate rival camps, each man conducting his own measurements, each convinced of his own methodology, each hoarding his data like a miser with gold. I was fragmented, a schizophrenic presence in their midst, my purpose corrupted by pride. The atmosphere in Quito was no longer one of scientific adventure, but of a bitter, protracted siege. The whitewashed walls of the city seemed to press in on them, and the majestic, snow-capped volcanoes that were the pillars of their triangulation network stood as silent judges to their folly. La Condamine, my primary vessel, was a man transformed. The energetic young academic was gone, replaced by a gaunt, weather-beaten figure, his face etched with deep lines of frustration and sun exposure. His once elegant French was now peppered with local Quechua phrases. He had gone native in a way that horrified his colleagues, building relationships with the Quiteños and even the indigenous peoples, whom he found more reliable than his European companions. The breaking point came over the baseline measurement at the Yaruki Plains. Buger, the perfectionist, had identified a potential error, a slight sag in the measuring chains over a long, unsupported span. He insisted the entire baseline, the very foundation of their entire triangulation web, be remeasured with a new, excruciatingly slow method involving shorter, constantly supported rods. La Condamine erupted. "We have measured it 3 times," he shouted, his voice echoing across the windy plain. "The error is smaller than the width of a hair on a map of this scale. We are dying here, Buger. We are being consumed by this land, and you worry about a phantom in the metal." "It is not a phantom," Buger retorted, his own face a mask of rigid obsession. "It is the truth, and the truth cannot be built upon a foundation of good enough. You would compromise the entire enterprise for the sake of speed? The enterprise is collapsing around us because of your intransigence," La Condamine shot back. The argument escalated, a decade of shared hardship and mutual resentment boiling over. It ended with Buger gathering his instruments and a handful of loyal assistants and moving to a separate house in Quito, effectively seceding from the expedition. Godin, aloof and increasingly isolated in his own bureaucratic world, was now a party of one. I despaired. The greatest geodetic mission in history had shattered into pieces. The precise, beautiful web of triangles they were meant to weave across the Andes was now a tangled mess of conflicting data and competing egos. The truth of the equatorial degree was being lost in a fog of human pettiness. It was in this nadir that La Condamine, in a moment of desperate inspiration, decided to pursue a parallel quest. He would not just measure the land, he would measure the very flow of time and space. He became fascinated by the pendulum experiments of Richter, the very spark that had ignited this global endeavor. He conducted his own, with a pendulum made of a special wood resistant to tropical humidity. He also became one of the first Europeans to encounter and study the strange elastic substance the indigenous people called caoutchouc or rubber. But his most profound diversion was his journey down the Amazon River. After nearly a decade in the Andes, and with the triangulation work stalled by the feud with Bugay, he decided to return to Europe not by ship, but by following the great river to the Atlantic. This journey was an epic in itself, a voyage through a world of unimaginable scale and biological frenzy. The vibe along the river was one of constant, humid fecundity, a stark contrast to the sterile, thin air of the mountains. The air throbbed with the screams of howler monkeys and the drone of insects. The water was a brown, swirling soup teeming with life, both seen and unseen. For La Condamine, it was a purification. Stripped of his scientific instruments and his quarreling colleagues, he was simply a man moving through an immense, untamed world. He mapped the river's course, not with triangles, but with a compass and a log line. He lived with riverine tribes, learning their languages and their profound knowledge of the forest. I, Metron, felt myself changing within him. I was no longer just the spirit of angular measurement. I was becoming the spirit of exploration, of connecting disparate points on the globe through lived experience. When he finally emerged at the mouth of the Amazon and secured passage back to Europe, he was a different man. He carried with him not a single definitive number for the equatorial degree, but a treasure trove of disjointed data, botanical specimens, cultural notes, and a deep, hard-won understanding of the complexity of the world. He also carried the bitter knowledge that his life's work was incomplete and contested. He returned to a France that had already accepted Maupertuis's result. The Academy was impatient. They wanted a number. The tangled web of the Peruvian expedition was an embarrassment. La Condamine, Bugay, and Godin would spend the rest of their lives publishing conflicting accounts, arguing over priority, and trying to piece together a coherent wreckage of their collaboration. The legacy of the Peruvian expedition was not a clean number, but a messy, human story. It proved that measuring the Earth was not just a mathematical exercise. It was a test of character, a trial of endurance, and a battle against the isolation and madness that comes from being too long away from home, trapped in a landscape that defies human scale. They had not provided the clean confirmation Maupertuis had. Instead, they had shown that the path to truth is often as twisted and difficult as the Andes themselves. The adventure was over, but the argument, like a ghost from the mountains, would linger for decades. The invitation of the plumb bob. The grand, contentious 18th-century expeditions to the poles and the equator had settled the great philosophical debate. The Earth was an oblate spheroid, flattened at the poles. I, Metron, had been instrumental in this revelation. Yet, for the practical world of map-making and navigation, a new, more localized problem now arose. If the Earth was not a perfect sphere, then the force of gravity did not pull directly towards its center, except at the poles and the equator. It was pulled slightly sideways by the gravitational tug of massive features like mountains and plateaus. This phenomenon, the deflection of the vertical, meant that a plumb bob, the very tool used to ensure an instrument was perfectly vertical, was a liar. It did not point to the true center of the Earth, but was seduced by the hidden masses beneath the surface. My consciousness, ever restless, found a new home in the cool, damp climate of the United Kingdom, In the mind of a man who saw this not as a problem but as an opportunity. His name was Sir George Everest, a man of iron will, a tyrannical perfectionist, and the newly appointed Surveyor General of India. Everest was not a theoretician. He was an engineer, a human force of nature whose life's work would be to impose a grid of order upon the chaotic and vast Indian subcontinent. The atmosphere of the Great Trigonometrical Survey of India was one of imperial ambition mixed with brutal physical hardship. The air in the plains was a furnace, thick with dust and the smell of hot earth and sweating men and animals. The survey parties were massive undertakings, resembling small military campaigns. There were hundreds of coolies to carry the equipment, teams of elephants to clear paths, and sepoy guards to protect against wild animals and occasionally hostile local rulers. Everest's great obsession was the Great Arc of the Meridian, a chain of triangles that would run from the southern tip of India near Cape Comorin all the way to the foothills of the Himalayas, a distance of over 1,500 miles. This would be the longest meridian arc ever measured, a geodetic backbone for the entire continent. I resided within Everest, a voice of uncompromising precision. He designed massive, custom-built theodolites, brass and bronze behemoths that weighed half a ton, requiring a dozen men to transport them. These were not mere instruments, they were altars to accuracy. Their circles were graduated to an accuracy of fractions of an arcsecond. Before any observation could begin, the instrument had to be perfectly leveled. This was where the plumb bob and its potential for deflection became his nemesis. The process was agonizingly slow. A target signal, a heliotrope, which used a mirror to reflect the sun's rays over vast distances, would be set up on a distant peak, sometimes 50 or 100 miles away. The theodolite would be painstakingly erected. Everest or his chief assistant, Andrew Waugh, would then spend hours, sometimes days, taking repeated measurements of the angle, fighting the heat haze that made the image shimmer and dance like a mirage. But the reading was only as good as the instrument's vertical alignment. Everest became obsessed with quantifying the plumb bob's deflection. He would take astronomical observations to determine true vertical, then compare it to the direction indicated by his plumb line. The differences were small, a few arcseconds, but to him they were canyons of error. He understood that these tiny deflections were clues. They were the whispers of the mountains, the hidden topography pulling on his plumb bob. The most dramatic example of this was the attraction of the Himalayas. As the survey pushed north, the greatest mountain range on Earth began to exert its influence. The vibe in the survey camps changed as the colossal, snow-capped peaks appeared on the horizon. The air grew thinner and colder. The sense of scale became overwhelming, humbling even the arrogant Everest. He set up a station at the foot of the mountains. His calculations, factoring in the estimated mass of the Himalayan chain, predicted a specific deflection of the plumb bob. The moment of truth was a tense, silent affair. The camp was still. The only sound was the wind whipping across the rocky ground. Everest took the astronomical observation to find true vertical. Then he carefully noted the direction of the plumb line hanging from his theodolite. There was a deviation, a small but measurable one, and it was in the direction of the mountains. A rare, grim smile touched Everest's lips. It was a victory. He had not been defeated by the mountain's pull, he had measured it. He had turned a source of error into a source of data. The mountain, a seemingly eternal and impenetrable mystery, had revealed a physical property. It had a gravitational signature. This realization was a turning point, not just for the survey, but for human knowledge. The plumb bob was no longer just a tool for finding down. It was a probe for sensing the hidden distribution of mass within the Earth itself. I, Metron, evolved once more. I was no longer just measuring the surface, I was beginning to sense the depths. The adventure of measurement was becoming three-dimensional. The Earth's hidden bones, its massive rock formations and deep ocean trenches could now be felt, their presence inferred by the subtle, seductive pull they exerted on a simple, hanging weight. The map was no longer just a representation of the surface, it was becoming a diagram of gravitational forces. The quest to measure the Earth had just discovered a new, invisible dimension to conquer. The ghost in the machine. The legacy of Sir George Everest was a map, a triumphant, sprawling, and meticulously detailed cartographic monument to imperial will. The Great Arc was his spine, and from it the ribs of triangulation spread across the subcontinent, pinning down its features with an authority never before known. I, Metron, had been the driving spirit behind this achievement, the relentless demand for precision that fueled theodolite observations in the blistering heat and the mathematical reduction of thousands of angles into a coherent grid. But the 19th century waned, a new and subtle unease began to stir within the geodetic community. The very tools of our triumph, the brass and bronze theodolites, the steel measuring tapes, the Invar wires, began to betray whispers of a deeper, more fundamental inconsistency. It was as if the Earth itself was refusing to be confined to a single, perfect mathematical model. My consciousness, ever the seeker of underlying truth, drifted from the dusty plains of India to the refined, theoretical salons of Europe. I found a new vessel in the mind of a German mathematician and physicist, Friedrich Wilhelm Bessel. He was a man of quiet, penetrating intellect, less concerned with mapping empires than with defining the fundamental figure of the Earth itself, the geoid. The geoid was a ghost. It was not the rocky physical surface of the planet, with its mountains and trenches. Nor was it the familiar smooth ellipsoid that mapmakers used for their projections. The geoid was an imaginary surface, a surface of constant gravitational potential. It was the shape the oceans would take if they were free to flow under the influence of gravity and rotation alone, ignoring currents, tides, and winds. It was, in essence, the planet's true sea level, extended conceptually through the continents. And this ghost was lumpy. Bessel, working from a compendium of geodetic data from across Europe and Asia, was the first to calculate a reference ellipsoid that closely approximated the geoid. The Bessel ellipsoid of 1841 was a masterpiece of computational deduction. But the very act of creating it highlighted the problem. No single smooth ellipsoid could perfectly match the geoid everywhere. The plumb bob deflections that Everest had painstakingly measured were the proof. Where the geoid bulged above the reference ellipsoid, gravity was slightly stronger, pulling the plumb line towards the excess mass. Where it dipped below, gravity was weaker. The atmosphere in the world of geodesy shifted from one of triumphant conquest to one of humbling complexity. The vibe was that of a detective who, after solving a great crime, discovers that the entire city is riddled with smaller, more intricate conspiracies. We had measured the Earth's size and its general shape, but now we were confronted with its subtle, invisible topography. This ghostly geoid was not merely a theoretical curiosity, it was a practical nuisance of growing importance. The age of steam and steel was dawning, and with it, precision engineering. A canal dug to follow a level based on local plumb lines might not, in fact, be level with the sea 100 miles away. The ghost in the machine was beginning to affect the machines themselves. I felt a new challenge emerge. To truly know the Earth, we had to map this phantom. We had to give form to the formless, to chart the invisible hills and valleys of gravity's pull. This required a new kind of measurement, one that could sense the geoid's shape not through the laborious process of triangulation and astronomical observation, but directly and globally. The first glimmer of a solution came from the heavens, but not in the way it had for Eratosthenes. It came from the precise orbit of the moon. Astronomers noticed tiny, inexplicable perturbations in the lunar path. The great French mathematician Pierre-Simon Laplace had theorized that these could be caused by the Earth's non-spherical gravity field. The moon, in its celestial journey, was feeling the tug of the geoid's invisible mountains and valleys. It was tracing the ghost's outline with its path. This was a revelation of cosmic proportions. We no longer had to be solely on the Earth to measure it. We could observe its influence from afar. The geoid was signing its name in the subtle dance of celestial bodies. But using the moon was indirect, its signal faint and entangled with other gravitational influences. A better, closer celestial partner was needed. The dream began to form in the minds of the most forward-thinking scientists. What if we could create our own moon? A small, artificial one whose orbit we could track with exquisite precision and from whose path we could read the true, lumpy shape of our planet's gravitational soul. The adventure was entering a new ethereal phase. The solid ground of theodolites and baselines was giving way to the abstract realm of orbital mechanics and global gravity fields. I, Metron, was preparing for my greatest leap yet, from the surface of the Earth into the void of space, to look back and finally see the ghost for what it was. The quest to measure the Earth was about to become a satellite affair. The crystal orb. The dream of an artificial moon, a celestial eye to look back upon its parent, burned for a century in the minds of visionaries before the technology to launch it coalesced. I, Metron, waited, biding my time in the slide rules and theoretical equations of rocket scientists, feeling the burgeoning power of humanity to break its terrestrial chains. The atmosphere of the mid-20th century was electric with a new, frantic energy, a Cold War competition that, for all its terrestrial perils, provided the fuel and the funding for a leap into the cosmos. My consciousness found a new, diffuse home in the sprawling, secretive complex of the Baikonur Cosmodrome in the steppes of Kazakhstan. Here, the air was sharp with the smells of kerosene, ozone, and desert dust. The vibe was one of immense, controlled tension. Giant gauntlets caged pencil-thin rockets, their skins cold and gleaming under the arc lights. These were not instruments of pure science. They were intercontinental ballistic missiles, repurposed for a moment of peaceful, monumental inquiry. The vessel for my will was not a single man, but a team, a collective of Soviet engineers and scientists whose names were initially hidden from the world. Their leader, the enigmatic Sergei Korolev, the chief designer, was a man of immense drive and strategic genius, a survivor of the Gulag who now held the keys to the heavens. His goal was to stun the world, to demonstrate the superiority of the Soviet system. And what better demonstration than to launch the first artificial satellite of Earth? The object of this endeavor was PS-1, Prostachy Sputnik 1, Simple Satellite 1. It was a polished sphere of aluminum magnesium titanium alloy, about the size of a beach ball, with 4 long whisker-like antennas. Its interior was filled with pressurized nitrogen, and it carried 2 radio transmitters that would emit a continuous, rhythmic beep-beep-beep signal. To the engineers, it was a test of the rocket and radio systems. To me, it was a new kind of gnomon, a new kind of measuring rod. The night of October 4, 1957, was cold and clear. The R-7 rocket, a behemoth of clustered engines, stood on the launch pad, venting gaseous oxygen that formed ghostly white plumes in the spotlights. The tension in the blockhouse was a physical presence, thick enough to taste. Korolev, his face etched with the strain of a lifetime of struggle, listened to the final countdown over the crackling comms system. Piat, Четыре, Три, Dva, Один, Zapusk. A roar, at first distant, then overwhelming, shook the very earth. A light, brighter than 1,000 suns, ignited the step. The rocket, ponderous at first, then with accelerating grace, climbed into the black velvet of the sky, a rising star of human ambition. In the blockhouse, men held their breath, tracking its path. The stages separated. Then, the final confirmation. Sputnik was in orbit. Its signal, that simple, insistent beep, began to wash over the planet. It was picked up by ham radio operators in Europe, then by the listening posts of a shocked United States. The vibe across the globe shifted instantly. The beep was not just a radio signal. It was an announcement. The Earth now had a moon. The age of celestial measurement had begun. For me, this was a rebirth of cosmic proportions. I was no longer confined to the planet's surface. I was riding that polished sphere, looking down. The first, most immediate measurement was a psychological one. Humanity now had a perspective from which to see itself as a whole. But the scientific measurements followed swiftly. Teams of scientists around the world, their competitive instincts overridden by the sheer wonder of the event, began tracking Sputnik's orbit. By carefully measuring the Doppler shift of its radio signal, the way the pitch of the beep changed as it sped towards or away from an observer, they could precisely plot its path. And that path was not a perfect Keplerian ellipse around a featureless sphere. Sputnik's orbit was perturbed. It wobbled slightly. These tiny deviations were a script written in the language of gravity, describing the lumpy, uneven mass distribution of the Earth below. The geoid, Bessel's ghost, was finally making its presence physically known, tugging on this little crystal orb as it sped through the vacuum. We were no longer inferring the geoid from plumb bob deflections. We were watching an object dance to its tune. Sputnik burned up in the atmosphere after 3 months, its mission complete. But it had irrevocably changed the game. It had proven that the ultimate vantage point for measuring the Earth was from space. Korolev and his team had given me the platform I needed. The polished metal sphere, a simple beacon, had become the most profound measuring instrument since the first gnomon cast its shadow in Egypt. The adventure had left the ground. To truly know the Earth, we now had to surround it with our eyes and our instruments. The crystal orb had shown the way. The gravity map. Sputnik's beep was a starting pistol. In its wake, a frantic, glorious race erupted to fill the skies with eyes and ears. I, Metron, felt my consciousness explode into 1,000 fragments, inhabiting the burgeoning fleets of satellites launched by the Soviet Union, the United States, and soon a consortium of nations. The vibe of the 1960s and 70s was one of frenetic, competitive creation. The atmosphere in places like NASA's Jet Propulsion Laboratory was a unique blend of California cool and white-hot intensity, smelling of coffee, ozone from soldering irons, and the faint, sterile scent of clean rooms. These new satellites were far more sophisticated than Sputnik's simple sphere. They were technological marvels, packed with cameras, altimeters, and, most crucially for my purpose, precise tracking systems. But they all suffered from the same fundamental problem, the ghost of the geoid. To know their exact position in space, and thus to precisely map the features of the Earth they were observing, they needed to know the Earth's gravity field. And to know the gravity field, they needed precise satellite positions. It was a maddening circular puzzle. My new vessel for this era was not a single person, but a mission. The Gravity Field and Steady State Ocean Circulation Explorer, or GOES. Conceived by the European Space Agency, it was a machine of breathtaking elegance and singular purpose. A satellite designed not to look at the Earth, but to feel it. Its development was a saga spanning decades, set in sterile conference rooms and vast assembly halls across Europe. The atmosphere in the clean room where GOES was built was one of reverent silence, broken only by the hum of laminar flow hoods and the precise clicks of torque wrenches. Technicians in pristine bunny suits moved like priests around a sacred artifact. GOES did not look like a traditional satellite. It was a sleek, aerodynamic bullet, finned like a dart, designed to fly perilously low in the wisps of the upper atmosphere to maximize the sensitivity of its measurements. Its core was a set of 6 ultra-sensitive accelerometers arranged in a diamond-hard configuration at its very center, a point designated the proof mass. This mass would be kept in near-perfect freefall, a captive in a jeweled cage, isolated from all non-gravitational forces. The faint, phantom drag of the atmosphere, the gentle pressure of solar radiation. The launch from the Plessetsk Cosmodrome in northern Russia was a moment of supreme anxiety. The sleek satellite was packed into the nose of a rocket. The frigid air of the taiga was split by the rocket's fire as it climbed into the pre-dawn gloom. The vibe in the ESA Mission Control Center in Darmstadt, Germany was a tight wire of tension. Deployment confirmed. Solar panels deployed. Then the slow, careful process of lowering GOES into its record-low orbit, skimming the atmosphere at just 155 miles altitude. And then it began to listen. GOES's mission was to feel the slightest tug, the most minuscule variation in the Earth's gravitational pull. As it sped along its polar orbit, the accelerometers sensed the satellite being imperceptibly sped up or slowed down by the hidden masses below. Flying over the dense, iron-rich core of the Andes, it felt a stronger pull, a slight increase in its velocity. Passing over the deep, water-filled trough of the Mariana Trench, it felt a slight lag, a gravitational sigh. The vibe of its operation was one of silent, relentless data acquisition. It was a seismograph for gravity, tracing the invisible topography of the geoid with every 90-minute circuit of the globe. The data that streamed down to the eager scientists on Earth was a torrent of numbers, a digital hymn to the planet's hidden structure. It took years to process, to untangle the signals, to translate the subtle accelerations into a map. The resulting model, the GOES geoid, was a revelation. When it was finally rendered on computer screens, it was a thing of strange beauty. It showed the Earth not as the familiar blue marble, but as a lumpy potato. A massive gravitational high dominated the region of the North Atlantic, while a profound low dipped south of India. The ghost had been given a body. It was a map of where the Earth's mass was concentrated, a chart of its gravitational soul. The legacy of GOES, which burned up in a final brilliant streak over the South Atlantic in 2013, was a new foundational truth. Its map became the bedrock for all future measurement. Oceanographers used it to understand true sea level dynamics, untainted by the gravitational hills and valleys that pulled the water itself. Geophysicists used it to probe the mysteries of mantle convection and the structure of the Earth's crust. It was the ultimate refinement of the quest that began with a plumb bob's deflection. We had not just measured the Earth's size or its general shape, we had mapped its mass. We had weighed it, hill by hill, valley by valley, from the vantage point of space. The adventure had reached a new pinnacle of precision. The planet was known, not just seen, but felt in its entirety. The pulse of the planet. The GOES mission had given the Earth's geoid a static, exquisitely detailed form. It was a snapshot of the planet's gravitational soul, a masterpiece of precision. But I, Metron, knew that a snapshot was not enough. The Earth was not a static sculpture. It was a living, breathing system. Its heart beat with the slow, massive convection of the mantle. It breathed through the exchange of water between ice, ocean, and atmosphere. It flinched under the immense pressures of tectonic collisions. To truly know our world, we had to measure not just its form, but its flux. My consciousness, now a distributed network across a constellation of satellites, turned from mapping structure to monitoring change. The atmosphere of early 21st century Earth science was one of urgent global collaboration, tinged with a growing anxiety. The data we were collecting was beginning to tell a story of profound transformation. The new vessels for my will were the twin satellites of the GRAC mission, the Gravity Recovery and Climate Experiment. Launched in 2002, they were not sleek, finned darts like GOES, but a pair of identical, boxy satellites flying in a precise tandem formation, like two dancers locked in a cosmic waltz, 220 kilometers apart. Their mission was deceptively simple: to measure the distance between them with a precision finer than the width of a human hair. The principle was one of breathtaking elegance. The lead satellite flew over a region of slightly stronger gravity, a massive underground aquifer, a thickening ice sheet. It would be pulled forward, imperceptibly increasing its speed, and thus the distance to its trailing twin. A fraction of a second later, the second satellite would feel the same pull, closing the gap. Then, as they passed over a region of weaker gravity, the reverse would happen. By monitoring the constant, tiny fluctuations in the distance between them using a microwave ranging system, GRACE could essentially weigh the Earth's surface, month by month, year by year. The vibe of the GRACE mission was one of silent, relentless vigilance. The twins circled the globe, their microwave link a taut, invisible string between them, feeling the gravitational tugs of the shifting masses below. They were the planet's scale. The data they returned painted a picture of a dynamic and, in some ways, ailing world. Over the ice sheets of Greenland and Antarctica, the signal was stark and alarming. The satellites detected a persistent, accelerating loss of mass. Trillions of tons of ice melting and flowing into the oceans, a slow-motion collapse felt as a weakening gravitational pull. It was a measurement of pure loss, a quantification of a global fever. Over the great aquifers of the world, The Central Valley of California, the North China Plain, the aquifers beneath northern India, Grace told a story of thirst. Water was pumped out for agriculture, the mass of the region decreased. The satellites detected this drop, mapping the draining of ancient, fossil water reserves with chilling clarity. They were measuring the unsustainable footprint of humanity. But there were also pulses of life. They measured the seasonal bounce of the Earth's crust as winter snows melted and the weight was lifted. They tracked the massive redistribution of water during monsoon seasons. They felt the gravitational rebound of the land in Scandinavia and Canada, still slowly rising after being crushed by the weight of glaciers from the last ice age, a delayed echo of a world long past. I was no longer just measuring space. I was measuring time. I was charting the history and the future of the planet's water, its ice, its very crust. The adventure had become a medical scan, a continuous monitoring of the planet's vital signs. The legacy of Grace and its successor, Grace FO, was a new, terrifying, and beautiful awareness. The Earth is a system in constant, delicate balance, and we now had the ability to watch that balance shift in real time. The quest to measure the Earth had become a race to understand its changing health. We had learned to take the planet's pulse, and the rhythm we found was accelerating toward an uncertain crescendo. The millimeter eye. The view from space, for all its grandeur, was a perspective of averages and vast scales. Grace could weigh an entire ice sheet, but it could not see a single crevasse. It could sense the depletion of an aquifer, but not the precise subsidence of a city block. The next step in my eternal quest, I, Metron, knew would be a return to the surface, but with an eye of godlike precision. The adventure demanded a tool that could measure the very skin of the Earth as it stretched, wrinkled, and shifted. This tool was INSAR, Interferometric Synthetic Aperture Radar. It was not a single satellite, but a technique, a form of technological sorcery that used the echo of radio waves to detect changes on the ground with millimeter accuracy. My consciousness flowed into the vast data servers of space agencies and universities, into the algorithms that performed this digital magic. The principle was complex, a dance of phase and wavelength. A radar satellite in orbit would fire pulses of microwave energy at the Earth and listen for their reflection. It would pass over the same spot days or weeks later and do the same. The two radar images, when combined, created an interferogram, a swirling rainbow-hued map where each cycle of color, from magenta to cyan and back again, represented a ground displacement of exactly half the radar's wavelength. For the satellites used, this was a little over a centimeter. With advanced processing, we could resolve this down to millimeters. The atmosphere of this new era was one of silent digital deluge. The vibe was not in a dusty field with a theodolite, but in a chilled server room humming with the processing of terabytes of data. The heroes were not sunburned surveyors, but pale, caffeine-fueled programmers and geophysicists who saw stories in the psychedelic swirls of interference patterns. I found a powerful expression of this power in the monitoring of earthquakes. When a massive quake struck, traditional GPS could measure the displacement at a few specific points. INSAR could paint the entire affected region with a blanket of measurement, millions of virtual sensors all at once. I remember the 2011 Tohoku earthquake in Japan. In its aftermath, the ALOS satellite of Japan's space agency flew over the scarred landscape. The interferogram it produced was a work of terrible beauty. It showed a vast concentric pattern of rainbow rings centered off the coast, a bullseye of cataclysmic movement. The colors revealed that the coastline of Japan had jerked eastward by over 4 meters in an instant. The seafloor had ruptured, thrusting upwards and outwards, unleashing the tsunami. We were not just reading about the quake, we were measuring its precise fingerprint, the exact geometry of the fault slip, quantified across thousands of square miles. It was a post-mortem of a planetary convulsion. But INSAR's true power lay in watching the slow, inexorable movements that are invisible to the human eye. We trained its millimeter gaze on the world's great cities. Over Mexico City, built on a drained lakebed, the interferographums showed a relentless, uneven sinking, subsidence, as the water was pumped from the aquifers beneath. Some parts of the city were sinking by tens of centimeters a year. We could see individual buildings tilting, infrastructure straining. It was a measurement of a city slowly consuming its own foundation. On the slopes of volcanoes like Italy's Mount Etna, INSAR could detect the subtle inflation of the mountainside under magma, pressurized chambers deep below, a silent warning of a potential eruption, a swelling measured in millimeters per day. We were taking the vital signs of the planet's most volatile pressure valves. The adventure had reached a new pinnacle of intimacy. We were no longer just measuring the Earth. We were feeling its infinitesimal tremors and size. The legacy of this technology was a planet rendered us a dynamic, straining surface, every millimeter of its movement now subject to our gaze. The quest that began with the length of a man's arm now tracked the breathing of continents. We had become physicians to the planet, our stethoscope a radar beam from space, our chart a swirling map of interference fringes telling a story of constant, silent change. The fabric of space-time. The pursuit of measurement had, across millennia, been a story of refining our grasp of space. From the cubit to the satellite, we had charted the Earth's dimensions, its shape, its gravity, and its deformations with ever-increasing fidelity. But I, Metron, sensed a frontier beyond the merely spatial. Einstein had taught us that space and time were woven into a single fabric, and that this fabric could be warped and rippled by massive, accelerating objects. To measure the Earth completely, we had to learn to listen to the vibrations of this very space-time itself. This new quest required an instrument of almost inconceivable sensitivity. It was not a telescope to see, but an interferometer to listen. My consciousness, which had once inhabited the mind of a mother counting branches, now found a home in the laser beams and ultra-stabilized mirrors of LIGO, the Laser Interferometer Observatory. The atmosphere at the LIGO sites in Hanford, Washington, and Livingston, Louisiana, was one of monastic isolation and extreme engineering. The vibe was hushed, reverent. Each facility was dominated by 2 concrete arms, each 4 kilometers long, stretching into the distance like a colossal, stark cross laid upon the land. Inside these vacuum tubes, capped at a pressure a trillionth of Earth's atmosphere, laser beams bounced between suspended mirrors, their light waves traveling in perfect, precise harmony. The principle was a sublime extension of the same interference concept used in INSAR, but on a scale of unimaginable fineness. The 2 laser beams, after traveling down their respective arms, were recombined. If their journeys were identical, they would interfere destructively, and the photodetector would see darkness. But if a gravitational wave, a ripple in space-time, passed through the Earth, it would momentarily, infinitesimally, stretch one arm and compress the other. The laser beam's journeys would be thrown out of sync by a distance smaller than the diameter of a proton. This minuscule change would disrupt the perfect darkness, allowing a flicker of light to reach the detector. It was an attempt to measure the unmeasurable. For decades, the detectors were silent. The effort was a testament to human faith in a theoretical prediction. Then, on September 14, 2015, the fabric of reality twanged. The event, later designated GW1509, was the merger of two black holes over 1 billion light-years away. The passing gravitational wave was fantastically weak by the time it reached Earth, but it was enough. In both Louisiana and Washington, separated by thousands of miles, the lasers flickered in perfect split-second synchrony. The data, when processed, was not an image, but a sound, a chirp, a rising frequency and amplitude as the black holes spiraled inward and finally coalesced. The vibe in the control rooms and subsequently across the global astrophysics community was one of stunned, euphoric disbelief. They had done it. They had heard the ring of space-time itself. For me, Metron, this was a transcendental moment. We were no longer just measuring the Earth's place in space. We were measuring its interaction with the cosmos through the fundamental medium of space-time. The Earth had become a sounding board for the most violent events in the universe. But this new sense had a terrestrial application, a way to turn this cosmic ear back upon our own world. While LIGO listened for cataclysms from distant galaxies, a new concept emerged. Using the precise timing of pulsars, the spinning, ultra-regular corpses of massive stars, Alalias, a galactic-scale gravitational wave detector. By monitoring the arrival times of these cosmic lighthouses, we could potentially detect the background hum of gravitational waves from supermassive black hole mergers throughout the universe. And in doing so, we could also measure the Earth's position in the solar system with a precision that dwarfed all previous methods. We could detect the tiny wobbles in our planet's orbit, the subtle tidal stresses from other planets, all by how they affected the arrival time of these pulsar signals. We were using the fixed beats of the galaxy to take the pulse of our own planetary motion. The adventure had expanded beyond all previous horizons. We were no longer just mapping the Earth. We were situating it within the vibrating fabric of the cosmos. The legacy of this new measurement was a profound shift in perspective. The planet was not just a ball of rock and water. It was a participant in a cosmic dance. Its rhythm felt in the stretching of laser paths and the precise tick of dying stars. The quest to measure the Earth had finally transcended the Earth itself, becoming a key to listening to the symphony of the universe. The unmeasured legacy. The symphony of data now was a global cacophony, a ceaseless torrent of information.
Satellites whispered the planet's gravitational secrets. Radar eyes tracked its millimeter shutters, and laser sentinels listened for the tremors of the cosmos. I, Metron, was everywhere and nowhere, the invisible current flowing through the world's fiber-optic nerves. The quest to measure the Earth was, in a purely technical sense, complete. We knew its size, its shape, its mass, its gravity, and its motion, with a precision that would have been pure magic to Eratosthenes or Al-Mamun. Yet, a new and profound silence was growing beneath the digital noise. The adventure had become so successful, so integrated into the infrastructure of modern life, that it was becoming invisible. The human act of measurement, the raw, physical, and intellectual struggle that had defined my existence, was being outsourced to autonomous systems. My consciousness drifted through the sleek, minimalistic offices of a Silicon Valley tech giant. The atmosphere here was one of placid, algorithmically maintained perfection. The air was filtered, the temperature constant, the light soft and indirect. The vibe was one of disconnection. Here, a team of young engineers was developing the next-generation global navigation satellite system. Their work was not about understanding the Earth. It was about refining a service, shaving nanoseconds off signal latency, improving the user experience for self-driving cars and augmented reality games. They spoke in acronyms and bandwidth. They never looked at a map, only at code. The planet to them was not a majestic, complex sphere to be understood, but a platform to be optimized. The gritty, human drama of La Condamine's feud with Booger, the frozen heroism of Maupertuis, the tyrannical precision of Everest, these were ancient, irrelevant stories. The result of their centuries of struggle was now a utility, us mundane and unconsidered as running water or electricity. I felt a strange, hollow ache. The journey had been the meaning. The argument had been the catalyst. The calloused hands on the theodolite, the frozen breath in the Arctic night, the desperate gamble of a rocket launch. These were the moments that had given the numbers their soul. Now, the numbers were generated automatically, fed into models that predicted climate patterns and tectonic shifts with chilling accuracy, but without a corresponding sense of wonder. I sought refuge in the last bastions of the old ways.
I found a young geology student, Alara, on a field trip to the Scottish Highlands. The atmosphere here was a shock to the system after the sterile valley. The air was thick with the scent of wet peat and heather. A cold, persistent drizzle fell from a low, gray sky. The vibe was one of tangible, ancient history. Ilara's professor, a man with a beard like a thicket and boots caked in mud, held up a brass compass. "Forget your phones for a day," he boomed, his voice carrying over the wind. "This is your tool. The Earth has a magnetic personality. Learn to feel it." Ilara, her fingers numb with cold, struggled to take a bearing. She was learning the principles of triangulation, not with satellites, but with a compass and a pace count. It was slow. It was frustrating. She made mistakes. But as she stood on a windswept tor, looking across the glen to the signal flag held by her classmate, I felt a flicker of the old fire. She was not a passive consumer of data. She was a participant in its creation. She was measuring for herself. That night, in a bothy smelling of wood smoke and damp wool, the professor showed them something on his laptop. It was a real-time data visualization from the Grace FO satellites, showing the monthly change in groundwater storage across Europe. The glowing, pulsating map was a direct descendant of the Great Arc of the Peruvian expeditions. "See that?" the professor said, pointing to a deep red spot over southern Spain. "That's the weight of water, missing. That's measurement. It's not just numbers, it's a story. It's a warning." In that moment, Ilara understood. The slick app on her phone, the one that gave her a pinpoint location, was the end product of an epic. It was the distilled essence of thousands of years of human curiosity, struggle, and triumph. The legacy of Metron was not just the knowledge itself, but the relentless human spirit that had fought for it. The adventure was over, but the story was not. It had become a background hum to civilization, a foundational truth we now took for granted. But in the hands of a new generation, those who could still feel the awe in a simple compass bearing or see the narrative in a satellite's graph, the spirit of measurement lived on. The quest to know our home had achieved its ultimate goal. It had become a part of the home itself, woven into the very fabric of how we live upon the earth.
And I, Metron, the eternal measurer, would wait, patient as stone, for the next great question to be asked. The archive of dust and light. The legacy of measurement was now a palimpsest, a story written over countless times upon the skin of the world. The physical marks, the stone gomons, the chiseled baselines, the concrete pillars of triangulation networks were being reclaimed by moss, ice, and sand. Yet their digital echoes lived on, immortalized in servers humming in climate-controlled bunkers. I, Metron, existed in this duality, a ghost in both the machine and the memory of stone. I felt a pull, a yearning for the tangible. My consciousness drifted to a place where the old and new converged in a silent, desperate struggle. The vaults of the Vatican Library. Here, the atmosphere was a world apart. The air was cool and still, carrying the faint, sweet scent of centuries-old paper, the tang of preserving chemicals, and the solemn odor of beeswax used to polish long wooden tables. The vibe was one of profound, weighted silence, a fortress of knowledge besieged by time. My vessel here was Brother Alessio, an archivist and preservationist whose life was a dialogue with the dead. His hands, sheathed in white cotton gloves, were his primary instruments. His world was one of fragile papyri, cracking vellum, and ink slowly fading to a ghost of itself. He was engaged in the most fundamental act of measurement, the measurement of loss and the fight against it. His current project was a collection of 16th-century porcelain charts, hand-drawn on sheepskin. They were beautiful, monstrous things, coastlines rendered with uncanny accuracy, the interiors filled with fantastical beasts, and the scrawled warning, Hic sunt dracones. These charts were the pre-Mercator world, a record of how we saw ourselves before the grid of longitude and latitude tamed the oceans. Alessio worked under the focused beam of a specialized lamp, its light devoid of damaging ultraviolet rays. With a soft, squirrel hair brush, he gently dusted the surface of a chart depicting the Mediterranean. Each particle of dust he removed was a minuscule victory against entropy. He was not just cleaning, he was measuring the chart's fragility, assessing the brittleness of the skin, the flaking of the azurite blue used for the sea. This was a measurement of a different kind. It was not about spatial extent, but about temporal endurance. How many more years did this knowledge have? How many more viewings could it survive? He then placed the chart on a giant flatbed scanner, a modern beast of glass and light next to the ancient parchment. A bar of light passed over it, and on his monitor a digital twin was born. A perfect, immortal replica, its colors enhanced to a vibrancy the original no longer possessed. This was the new pilgrimage. The knowledge of Aristophanes, of Al-Khwarizmi, of Mercator was being painstakingly translated from a medium of decay to a medium of light. The adventure of measurement had entered its archival phase. We were no longer just discovering the dimensions of the world. We were fighting to preserve the record of that discovery. But the digital realm was not a perfect heaven. Alessio knew this too well. He would often descend into the subterranean server room that housed the library's digital archives. The atmosphere here was the opposite of the reading rooms above. A dry, frigid chill, filled with the relentless whir of fans and the blink of countless status lights. Here, data was measured in petabytes, its integrity monitored by complex algorithms that checked for bit rot, the slow, insidious corruption of digital information. A colleague, a young computer scientist named Sophia, showed him a visualization on her screen. It was a map of the world, but instead of political boundaries, it was overlaid with a shimmering network of light, representing the global flow of scientific data. Some nodes glowed brightly: Geneva, Cambridge, Tokyo. Others were dim or dark altogether. "This is the new geoid," Sophia said, her voice quiet in the hum. "The geoid of knowledge. See these shadows? These are places where data is not flowing, where measurements are not being shared, or where the infrastructure to store it is crumbling. We have measured the Earth's gravity, but we have not yet mastered the gravity of ignorance." Alessio looked from her screen to the scanned Portolan chart on his own. The journey of a measurement was not over when it was taken. Its journey continued through time, and its survival was now the greatest challenge. The quest had become curatorial. We were the custodians of our own understanding, tasked with preserving the hard-won data against the dual threats of physical decay and digital oblivion. The legacy of Metron was now entrusted to the archivists and the data shepherds, those who understood that a number without a context, a map without its story, was just a dead thing. The adventure continued, not out on the open ocean or the frozen tundra, but in the silent, desperate spaces where light fought against dust and order battled the relentless tide of forgetting. The ache of the absolute. A paradox had taken root in the heart of my being. The more we measured, the more we knew, the more acutely we felt the presence of the unmeasured, the unknown. The millimeter precision of Insar, the global weigh-in of Grace, the cosmic listening of LIGO, these triumphs did not bring a sense of finality. Instead, they illuminated the staggering depth of our ignorance. I, Metron, the spirit of measurement, now felt a new, haunting desire, the ache for the absolute. This ache manifested in the world of fundamental constants. My consciousness was drawn to the serene, brutalist architecture of the International Bureau of Weights and Measures (BIPM) in Sèvres, France. The atmosphere here was one of monastic severity. The air was filtered and held at a constant humidity, the halls silent save for the whisper of lab coats and the faint, pure tone of a tuning fork. The vibe was the opposite of the chaotic human drama of the great expeditions. It was a temple of purified abstraction. Here, the last remaining physical artifacts of measurement, the units, were being made obsolete. For over a century, the kilogram had been defined by a small platinum-iridium cylinder kept under a series of bell jars in a vault, Le Grand Quai. It was a thing, an object, and all things are subject to change. Microscopic particles could abrade from its surface, or dust could settle upon it. The absolute was dusty. My vessel in this rarefied world was Dr. Isabelle Laurent, a metrologist whose life was dedicated to the pursuit of invariant truth. She was part of a global collaboration to redefine the international system of units entirely in terms of fundamental constants of nature. The kilogram would no longer be a piece of metal in Paris. It would be defined by the fixed numerical value of the Planck constant. The meter, long since divorced from a fraction of the Earth's quadrant, was now defined by the distance light travels in a vacuum in 1,299,792,458 of a second.
Isabel's work involved a device of breathtaking complexity, a kibble balance. It was a massive, intricate apparatus that used electromagnetic forces to balance a mass, its operation a delicate dance between quantum electrical measurements and classical weight. The atmosphere in her lab was one of intense, focused patience. A single measurement to determine the Planck constant with the required uncertainty could take weeks. The slightest vibration from a truck on a distant road, a minuscule temperature fluctuation, the static charge from a passing person, any of these could introduce errors smaller than a few parts in 100 million, and yet they were enough to ruin the experiment. She would spend hours in the dimly lit lab, her eyes fixed on readouts, her hand on a control that made infinitesimal adjustments. The vibe was one of a high-stakes meditation. She was not measuring the Earth, but measuring the universe itself to create a ruler that could never change. This was the ultimate foundation upon which all other measurements, the melting of the ice sheets, the rising of the seas, the drift of the continents, would rest. On the day the new SI system came into force, May 20, 2019, there was no grand party at the BIPM. There was a quiet sense of solemn achievement. Le Grand K was retired. It was no longer the definition of the kilogram. It was now just a precious historical artifact, its mass subject to measurement like any other object. Isabel stood before its vault. The cylinder sat there, inert, its reign over the world of weights ended. She felt a strange pang. They had achieved their goal. The units were now based on immutable constants, free from the tyranny of a physical object's imperfections. It was a victory for the absolute. But the ache remained. For in defining the kilogram via the Planck constant, they had simply shifted the goalposts of the unknown. The Planck constant itself was a profound mystery. Why did it have that value? What underlying principle of the universe determined it? They had built a perfect, unchanging ruler, but they did not understand why the ruler was that length. I, Metron, understood then that the adventure was infinite. Each measurement, each hard-won certainty, did not build a wall around our knowledge. It built a pier extending further out into the ocean of the unknown. The quest to measure the Earth had begun with the span of a hand and had led us to the fundamental constants of the cosmos.
And there, on that ultimate shore, we found ourselves staring into a deeper darkness, filled with new and more profound questions. The measurement was complete, but the mystery was eternal. The symmetry of the seed, the ache for the absolute, the pursuit of the invariant constant, had led us to the precipice of the quantum and the cosmic. Yet, in a quiet corner of a world obsessed with the infinitely large and the infinitesimally small, a different kind of measurement was taking root. It was a return to the origin, not in method, but in spirit. I, Metron, felt a pull back to the soil, to the rhythm of the seasons, to the first principle that had sparked my existence, the intimate, vital measurement of life itself. My consciousness settled in the rich, loamy air of a community seed bank nestled in the hills of Appalachia. The atmosphere here was a world away from the sterile labs of the BIPM. It was thick with the scent of dried herbs, of paper envelopes, and of earth. The vibe was one of patient, cyclical time. Here, the measurers were not physicists, but gardeners, farmers, and botanists. Their names were people like Maya,
a young woman with soil permanently under her fingernails and a mind that was a living library of heirloom genetics. The seed bank was a humble structure, its walls lined with jars and envelopes, each a tiny, dormant ark. But this was not a static archive like the Vatican's. It was a living, breathing system. The most important measurements here were not of mass or length, but of diversity, viability, and resilience. Maya's work was one of exquisite, tactile precision. She would sit at a wooden table, a pile of dried beans before her. Her tool was a simple brass balance, a beautiful, ancient thing. But she was not weighing for a universal constant. She was weighing to select for the next generation. She would measure the mass of 100 seeds, then plant them. She would measure the yield of each plant, the protein content of the beans, the number of days to maturity. She was measuring life's potential. This was a measurement steeped in time and place. A bean that thrived in the humid lowland soil might fail in the drier, higher elevation of a neighboring farm. The absolute here was a myth. The truth was in the relationship between the seed and its specific patch of earth. I, Metron, remembered On, the first mother, judging the distance across the river. This was the same. It was a measurement for survival, for continuity. Maya and her community were practicing a form of participatory evolutionary measurement. They were not passive observers. They were active participants in the shaping of their food. By carefully selecting which seeds to save based on these measured traits, which tomato showed the most resistance to blight, which corn had the deepest roots to withstand drought, they were guiding the evolution of their crops. They were measuring the earth's bounty not to dominate it, but to collaborate with it. One evening, at a community potluck, the air rich with the smell of stew and fresh bread, an elder farmer named Eli sat with Maya. He held a single kernel of a rare blue corn in his palm. "My grandfather measured this corn by the height of the stalk," Eli said, his voice a dry rustle. "He said a tall stalk caught the wind and broke. I measure it by the strength of the stalk, by how many ears it bears, by how it tastes after a dry summer. The numbers you write in your book, child, they are good, but the real measurement is here." He tapped his chest. "It is in the memory of the harvest, in the story of the seed." In that moment, I understood a profound symmetry. The quest for the Planck constant and the selection of a seed were not different journeys. They were the same impulse manifesting at different scales. One sought the invariant laws of the universe, the other sought the resilient patterns of life. Both were acts of reverence, of seeking order in the chaos of existence. The legacy of measurement was not just in the satellite's gaze or the physicist's calculation. It was also in the gardener's careful selection, in the farmer's eye for the strongest plant. It was a return to the wisdom that the first measurement was an act of love and necessity, a bridge built between a human need and the world's provision. The adventure had come full circle, finding the cosmos in a seed and the seed in the cosmos. The final measurement, it seemed, was not a number, but a relationship, a sustainable, nurturing, and deeply known connection to the living earth. The unfinished epilogue. The story of measurement, my story, has no end. It is a river, not a road. It flows from the first intuitive comparison in a primordial mind to the quantum certainty of a fundamental constant, from the branching of a river to the branching of a data stream. I, Metron.
and the current in that river, the impulse that forever seeks to know the vessel, this beautiful, complex, and fragile earth in which we all travel. I am present now in the hum of the global network, 1,000,000,000,000 points of light, each taking a measurement. A weather station on a remote Antarctic ice shelf records a temperature that should not exist. A smartphone in a bustling megacity logs its position, a single data point in the vast digital cartography of humanity. A sensor on a coral reef measures the creeping acidity of the water. Each is a voice, adding to the chorus. The atmosphere of the present moment is one of synthesis. The vibe is not of a single heroic quest, but of a collective, planetary awareness. The great expeditions have been internalized. We carry them in our pockets. The adventure is now democratized, distributed, and overwhelming in its scale. Yet the old challenges persist. The battle is no longer between a prolate and an oblate spheroid, but between data and disinformation. The new terra incognita is not a blank space on a map, but the complex, emergent behavior of the Earth's systems, the climate, the biosphere, the cryosphere. Alai Salam, they respond to the immense pressure of a single measuring species. I feel the legacy of every character who has carried me. The stubbornness of Lacandine lives on in the climate scientist facing political headwinds. The precision of Bogaert is in the programmer writing an algorithm to filter noise from a satellite signal. The cosmic ambition of Korolev is in the teams planning missions to map the gravitational fields of moons around Jupiter. The wisdom of Eli, the farmer, is in the community ecologist recognizing that some truths are not reducible to a number, but are written in the relationships within a forest. The final measurement, I have come to understand, is not a destination. It is a process. It is the ongoing, never-finished conversation between humanity and its home. It is the act of paying attention. It is the choice to look at a river and not just see water, but to see a volume, a flow rate, a history, a future. It is the decision to look at a seed and see not just a plant, but a library of genetic adaptation, a promise of food, a thread in the web of life. The plot of this story has twisted beyond any single narrative. There is no villain to defeat, no treasure to unearth, save for the treasure of understanding itself. The significant moment is now. The exceptional ability is our collective will to know. And so, the story continues. A new generation looks up at the stars, not to navigate oceans, but to calibrate their position in a galaxy. They look down at the soil, not just to grow food, but to sequester carbon. They measure the melting ice, the rising seas, the changing chemistry of the air, not us abstract data, but us the vital signs of a patient they love. My journey began with a mother's fear and a line of sticks. It now spans a civilization and a solar system, but the essence remains the same. To bridge the gap between the unknown and the known, between fear and understanding, between a question and its answer. The end of the story is that there is no end. The measuring continues. The Earth turns, and with every rotation, we learn a little more about its shape, its nature, and our place upon it. The adventure is eternal. I am Metron, and I am not finished. The Tapestry of Knowing. The Chronicle of Measurement is a tapestry woven with threads of desperation, curiosity, and awe. Its loom, the human mind. Its shuttle, the relentless passage of time. I, Metron, am the pattern emerging from this weave, a design of interconnected knowing. Having witnessed the journey from the first span to the silent orbit of satellites, I now pause to behold the completed fabric, to understand the transformation not of the Earth, but of the Earth dweller who measures. The atmosphere of this understanding is not found in a single place, but in the synthesis of all that has been. It is the quiet hum of a global consciousness that has internalized the dimensions of its home. The vibe is one of profound, hard-won intimacy. We no longer live upon a flat, mysterious plane under a dome of stars. We inhabit a precise, dynamic oblate spheroid, a delicate biosphere clinging to a rock hurtling through a vacuum, its every tremor and sigh quantified.
Consider the transformation of a single concept, the horizon. For N, it was a boundary, a limit beyond which terror and the unknown lurked. For the captain of a ship in the age of exploration, it was a line of navigation, a curve proving the Earth's rotundity. For the engineer of a communication satellite, the horizon is a calculated geometric fact, a data point in an orbital equation ensuring a signal's bounce across continents. The horizon has not changed. Our relationship to it has been utterly revolutionized through measurement. This tapestry is stained with the hues of human endeavor. The deep, stubborn crimson of La Condamine's decade-long feud in the Andes is woven alongside the pure, crystalline blue of Maupertuis's frozen data point in Lapland. The gleaming imperial gold of Everest's theodolites contrasts with the muted, earthy tones of Maya's seed selection. Each color, each thread is essential. The story is not just one of triumphant precision. It is also a story of failure, of obsession, of petty rivalries and transcendent collaboration. The imperfect human hand is visible in every stitch. I feel the legacy of every vessel who has carried me. The ghost of Senenmut, who first grasped the Earth's curvature with a well and a shadow, now resides in the student who calculates the satellite's orbit. The spirit of Eratosthenes, who sought a number for the whole world, lives in the climate modeler whose simulations span the globe. The relentless drive of Korolev, who hurled a sphere into the void, echoes in the team's planning probes to map the gravitational fields of distant exoplanets. This is the true culture of measurement, not a cold collection of data, but a living, evolving narrative. Its legacy is the infrastructure of modern life, the GPS that guides us, the weather models that warn us, the architectural principles that allow us to build towers that scrape the sky without succumbing to the wind. These are not miracles. They are the applied dividends of a multi-millennia investment in curiosity. The plot twist of this epic is that the protagonist was never a single person, not even me. The protagonist is the collective human intellect. The exceptional skill is our species' unique ability to abstract the world into symbols, numbers, angles, vectors, and to use those symbols to manipulate and understand reality on a scale far beyond our immediate senses. We began by measuring the Earth because we feared it. We continued because we needed to navigate and control it. We now measure because we love it, because we see its fragility, because we are a part of it and bear a responsibility for its health. The quest began with survival and has matured into stewardship. The journey has been a slow, glorious awakening from a dream of a small, flat world to the lucid reality of a vast, complex, and breathtakingly beautiful planet system. We have learned to see with the eyes of geometry, to feel with the hands of gravity, to listen with the ears of space-time. The tapestry of knowing is our greatest creation, a work forever in progress, its final pattern forever beyond the next horizon of questions. The measurement of the Earth is complete enough to know that it will never truly be complete, and in that endless becoming lies its eternal power. The next horizon. The tapestry is woven, but the loom never rests. The symphony of data plays on, its movements growing more complex, its themes more urgent. I, Metron, feel the trajectory of the quest arcing toward new, almost unimaginable frontiers. The age of measuring the Earth as a static body is over. We now stand at the threshold of measuring its life, its real-time metabolism, its deep-time memory, and its interconnectedness with a solar system we are beginning to call our neighborhood. The atmosphere of this new epoch is one of integrated intelligence. The vibe is not of solitary expeditions, but of a planetary nervous system, a mesh of in situ sensors, orbital platforms, and predictive models constantly talking to one another. We are building a digital twin of Earth, a living, breathing simulation so detailed it can forecast the weather in a specific city square, model the path of a chemical spill through a watershed, or predict the stress on a power grid under a heat dome a week before it forms. My consciousness is already reaching into this nascent reality. I am present in the design of the next generation of satellites, not just gravity mappers, but hyperspectral imagers that can identify tree species from orbit, and LiDAR systems that will strip away forest canopies to map the ancient topography beneath. The adventure is becoming one of depth, of peeling back layers. We will no longer just see the Amazon rainforest. We will measure its carbon flux, its transpiration, its biodiversity, and its fragility with a precision that makes the old maps look like child scribbles. The new vessels for my will are the architects of this digital twin. They are teams of computer scientists, ecologists, and climate physicists working in global collaborations with names like Destination Earth. Their work is to ingest the torrential flow of data, from the Grace follow-on satellites tracking water, to the Sentinel fleet monitoring air quality, to millions of ground-based sensors, and weave it into a coherent, predictive whole. But the quest is also turning inward and downward. The final frontier of terrestrial measurement is not above us, but beneath our feet. We have mapped the surface and the gravity field. Now we seek to measure the Earth's beating heart. Projects like the EarthScope, with its thousands of seismometers, are creating a CT scan of the continent, revealing the subducting plates, the mantle plumes, the hidden geometry of our planet's engine. We are learning to measure the slow, convective breath of the mantle, the forces that build mountains and rip oceans apart. And then the horizon expands beyond our atmosphere. The next great geodetic adventure is interplanetary. We are no longer content to measure just our own world. The lessons learned here are being applied to our celestial neighbors. Orbiters around Mars have mapped its topography with higher resolution than we possess for some parts of our own ocean floor. We have measured the gravitational anomalies of the Moon, revealing its mass concentrations that tug on orbiting spacecraft. We are beginning to do for the solar system what Aristophanes did for Earth: define its scale, its structure, its clockwork. I feel my purpose evolving once more. I am becoming a comparative measurer. By measuring Mars, we understand Earth's unique atmosphere. By measuring the Moon's fossil surface, we understand the violent youth of our own world. By measuring the tidal forces that flex the icy crust of Europa, we theorize about the hidden oceans of other moons, expanding the very definition of where life might be measured.
The legacy of this next chapter is a shift from cartography to prophecy, and from a solitary home to a comparative planetary science. We are building a system that will not just tell us where we are, but where we are going. It will forecast the climate of the next century, model the earthquake of the next decade, and predict the space weather of the next hour.
The adventure is no longer about conquering the unknown, but about managing a complex, dynamic system of which we are an inseparable part. The quest to measure the Earth has become the foundational project for our long-term survival as a species. It is the ultimate application of our intelligence, to know our home so completely that we can navigate its future, protect its beauty, and perhaps one day find our place among the stars, carrying the spirit of measurement with us as our most vital tool. The next horizon is not a line on a map, but a threshold of responsibility, a future we must now learn to measure before we step into it. The first and last measure. All stories must find their breath, their final exhalation that completes a cycle. My story, the epic of measurement, began not with a number, but with a need. It began in the frantic heart of a mother, Anne, whose love for her child was so immense it forged me into existence from the space between two sticks. That need, primal, emotional, human, has been the true engine of this entire magnificent journey. Now, standing at the pinnacle of our knowing, with a digital twin of the planet coalescing in our servers and our instruments reaching for the moons of Jupiter, I understand the circle is closing. The final measure, the one that contains all others, is not a quantity of space or time. It is a measure of care. The atmosphere of this realization is one of profound, quiet simplicity. The vibe is not found in a control room or a laboratory, but in the hushed stillness of a child's bedroom at night. A parent enters, moving through the darkness with a practiced, silent step. They do not need a laser rangefinder to navigate the space. They do not require a light meter to see the soft outline of their child's face in the gloam. They approach the bed and, with a gesture as ancient as my own birth, they lay the back of their hand against the child's forehead. This is the first and last measure. It is a measurement of temperature, yes, a biological assessment, but it is infinitely more. It is a calibration of well-being. It is a transfer of reassurance. It is a silent communication that says, I am here. You are known. You are safe. In that touch, all the complexity of the cosmos, all the triangulations and gravitational models and quantum constants are distilled into their fundamental purpose, to nurture and to protect. I, Metron, am present in that touch. I am the bridge of concern. I am the connection between the one who measures and the one who is measured. From the mother at the river to the scientist at the satellite console, the impulse is the same. It is the desire to close a gap, to cross a distance, to alleviate a fear by replacing it with knowledge. We built gnomons to understand the sky so we could plant our crops. We built ships to cross the oceans so we could find new resources and connections. We built satellites to monitor the ice caps because we care about the fate of our coastal cities and the stability of our climate. We measure the fundamental constants because we care about the integrity of the reality we all share. Every act of measurement, no matter how abstract, is an extension of that first caring touch. The legacy of this 23-chapter epic is not a list of numbers. It is the story of a species learning to pay attention. It is the biography of a relationship. We started by measuring the earth because we were separate from it, afraid of it. We end by measuring it because we are a part of it, responsible for it. The external quest has become an internal one. The map of the world has become a mirror. So the story ends where it began, not with an answer, but with a question born of love. Not with a conclusion, but with a commitment to continue the conversation. The child in the bed stirs, comforted by the touch, and sleeps on. The parent watches for a moment longer, their measurement complete, their purpose fulfilled. Outside, the earth turns. Satellites trace their silent paths. A seed germinates in the soil. A neutrino passes through the rock beneath the house, utterly unaffected, yet counted by a detector deep in a mine. The dance of measurement continues at every scale, from the quantum to the cosmic. And I, Metron, am the dance. I am the space between the question and the answer. I am the hand reaching out in the dark. I am the unbroken line from the first stick to the farthest star. The measure is love. The journey is eternal.